way through the morning talks. So there's been a change to the program. It was a few days ago, so you probably already know about it. Our first speaker this morning is our own inimitable Charlie Falco. Professor Falco is a professor of optics and physics at the University of Arizona. He's also the chair of condensed matter physics. He's a fellow of the American Physical Society, the Optical Society of America, the SBIE, the IEEE. He's published many, many papers, given even more invited talks at conferences, research institutes, and so on. However, he's much better known as a co-curator of the Guggenheim Museum's The Art of the Motorcycle exhibit. Had over 2 million visitors, and it was shown in New York, Chicago, Bilbao, Las Vegas. I think even the King of Spain's motorcycle was in the lineup. So apparently, well, I know this because Charlie told me, that this was the most successful exhibition of industrial design ever assembled. It's from his own CV, so it must be true. In any case, he has also admitted that far, far more people have read what he's written about motorcycles than all of his scientific papers together. So you never know where a hobby can lead, obviously, but you should follow your passion. So more recently, Charlie has been working with a famous artist by the name of David Hockney, and the two of them have found out something about Renaissance painters that caused apparently a fair amount of controversy and maybe even consternation. And we're going to hear about that this morning. Just to give you an idea, there have been entire international conferences organized around the so-called Falchi-Hockney thesis. Is that what it's called? Or is it Hockney-Falco?
I'm modestly said.
Okay. Anyway, most recently, Charlie was awarded the APS's Dwight Nicholson Medal for outreach, so it's very fitting to have him here today. Let's give him a big welcome.
Thank you for being here. As the session chair knows, 8:30 is not my time of day, and so I'll try to keep myself awake by talking fast and talking like I normally do. You'll see that there's great application to teaching optics, to getting students interested in optics through what I'm going to show you. And the only physics talks you'll ever hear that really deserves a fanfare of trumpets. So I'll tell you who David Hockney is as we go through. David Graves and Richard Smith are his assistants in London and his studio in Los Angeles. Jose Salcian is a professor here in optical sciences who did some ray tracing calculations for us early on that saved a lot of time. I'm not going to show those today, but certainly merits acknowledgement. Martin Kemp, now retired art historian, who actually was helpful in the way he misled David in understanding certain aspects of art history. And I'll tell you about multi-foil and Lawrence Weschler in a moment. So as an outline of what we're going to cover, and I'm going to talk very fast, and there's lots of information we're going to cover, and as we heard from yesterday's plenary speech, you're not going to remember any of this anyway. I purchased the domain name art-optics.com because you can remember that. And so all of our papers, PDFs of all of our papers, much more explanation is on the Optical Sciences website, whose URL nobody could possibly remember. And this will just bounce you directly to the URL. And some of you I know always are dyslexic, so I also purchased optics-art.com. And so you have no excuse not to remember to go there. And so I'm going to go very fast, and you go there for all the information. So I'm going to give you a general introduction and tell you about optics at the dawn of the Renaissance, of what was known. And then I'm going to remind you of optics that you know, but it turns out I'm not going to quiz you, unlike yesterday's speaker, because even though you're physicists, optical sciences students, optical sciences professors, there are actually some optics I find that professionals don't know. And I won't question you on that. I'll just tell you, and you can go, yeah, I knew that. And then I'm going to show you optical evidence within selected paintings, and there's only a limited amount of time, so I'm going to go fast through that. I'm only going to show a couple of examples of different kinds of optical evidence in paintings that show that optical projections were used basically 200 years before Galileo in critical ways for artists to create their paintings. And then sometime just before noon, I will come to the conclusions. So as an introduction, first, who is David Hockney, who I credit as co-author of this, rightfully so. And I should have pointed out, we're going to have some Windows 10 issues that nobody's yet been able to solve. That bar is cutting off critical stuff at the bottom of certain things, and I cannot get rid of it. And if anybody knows how to get rid of it, don't make suggestions like maybe you should try this. If you actually know how to get rid of that, tell me now, or tell me like if it's a right click and do something. I'd like to know it now, or tell me at the break. But so I'm sorry, it's just going to cut it off and blame Bill Gates for that. So David Hockney, by far the best known, most critically acclaimed British artist of his generation. The drawings or etchings are amongst the depths of the century. Posterity may record him as the greatest of modern portraitists. So he's a world-class artist. If there were a Nobel Prize in art, he certainly would be on the short list to be considered for it.
David Hockney, our most celebrated living artist.
He is considered to be one of Britain's greatest contemporary artists. His originality and skill have ensured his success from the beginning of his career.
But what's important for the purposes of this talk is something that's been obsessing David his entire career.
I admit, I'm interested in pictures. I keep saying this. I'm interested in
So if you look back, he's written about his art history interests, several points in his career. He did his training at the Royal Academy in London, and he's been looking at certain paintings that are in the National Gallery in London. And unlike many people in life, he hasn't understood something, and he doesn't go, I don't understand that, and goes on to something else. It bothers him. And scientists share this obsession, where maybe you've got some measurement you'd like to make, but it requires measuring nanovolts, and you can only buy microvolt meters at that point in your career. Later, you come back, you know, now they sell nanovolt meters, or I've figured out a way to make a nanovolt meter. I want to solve that problem that I had long ago that's been obsessing me. David's had that issue, and he's been thinking about how you make pictures. And so in 2000, an article appeared in the New Yorker talking about, by Lawrence Weschler, who I rightfully credit as being instrumental in helping this along. Ren Weschler wrote this article talking about David's early understanding of paintings. And he characterized paintings as being done one of two ways. Mostly like we think of, if I'm going to paint your portrait, I do like this, and he called that eyeballing. The other you call optical, but it was clear he didn't really understand what he meant by optical. My co-curator of the art of the motorcycle, Alton Guilfoyle, who at the time was the director of the filmmaking department at the Guggenheim, called me here in Tucson and said, Falco, I don't care what you're doing, drop it, go by the New Yorker, read that article, and call me back. New Yorker doesn't get to Tucson the same day it gets to Manhattan. So there was a pause of a couple of days. So I should be giving this talk to you 2 days ago, but because of that pause, I can only give it to you today. And this got me involved in the most intensive collaboration of my scientific career. And in fact, I have 7 reams of faxes now that David didn't do email in the early days. Everything came by fax. And so I collected together faxes, and that's a lot of material. 7 reams of faxes, 500 pages each. If we look back in art history, we go back 2,000 years BC, we see that that's a human, but it's flat, it's two-dimensional. Whoever drew that really wasn't very good, although they were way better than I can draw. I drew stick figures. We come forward in time, much more elaborate, but still flat, two-dimensional. We come to Jan van Eyck. If I magnify a portion of that figure, that is so realistic. If he walked in from around that corner, we'd immediately recognize them. How did Van Eyck do that? Well, there's a strong clue right in there. Every feature that I'm going to show you could have been done with optical projections, could have been done with one lens of a pair of spectacles. Someone my age wears reading glasses. The reading glasses typically are, if you go to the drugstore, you'll see a rack of reading glasses, and there's numbers. There's 1.5, 2, 2.5, and those aren't arbitrary numbers. They are the focal length in diopters. So 1 diopter is 1 over 1 meter. I don't know who invented this. But so 2 diopters is a 50 centimeter focal length lens. So someone my age has reading glasses that are probably about 2 diopters. Everything could be projected with that. Now, when I told you, art historians, when we first started doing this, art historians said they didn't have lenses back then. Well, I'm not an art historian. I didn't know. Okay, they didn't have lenses back then. Well, then I come across this painting. And I told this to actually a world-famous art historian on the East Coast. And she told me, well, we know that they had spectacles, but they didn't have lenses. I swear to you. So if you don't know that that's a lens, then you're out of luck. So I would say 99% of the people in the world don't know you could project an image with a pair of spectacles. And since you guys are all physicists and optical scientists, I'm not going to ask you if you believe that, because some of you didn't know that. And I'm not going to, point fingers and ask you to hold up fingers on that. Some of you didn't know that, now you do. And so I'm going to show you. There's a pair of spectacles from the drugstore, and my lab is on the 10th floor of another building, and looking down, projecting the image, the sky is below, the earth is above. So every projected image has that. What's not so obvious, since you don't know what the scene is the parity is reversed. Left and right are reversed. And we'll come to that in a minute. We look at attempts to represent three-dimensional objects in perspective. Well, you don't need to fit a perfect perspective-corrected hexagon to that to know that that doesn't fit. There's something wrong with that. We come back to Jan van Eyck. If I magnify that chandelier, it looks perfect. It's just excellent. What is not obvious is that chandelier, if you go to the real painting in the National Gallery, you could cover it with your cupped hand. So I've taken something that's this big, I've blown it up to be whatever, 10 feet across, and it's maintained its incredible fidelity. How did Van Eyck do that? There's a scale in there. And what I'll do is, after we made our discoveries, Marc Demey at the University of Ghent fit a perfect computer-generated ideal chandelier to the Van Eyck chandelier. We'll see how well it fits. Well, at first glance, it fits incredibly well. But if you look a little more closely, you'll see that he's off by a couple of millimeters, a couple widths of pencil lead. And what I'm going to show you as we go along is the fact that it fits so well, but not perfectly, also is consistent with an optical projection of a real object, not an object drawn using the laws of geometrical perspective, which had not been invented by then. So if I'm telling you that these things could have been based on optical projections, and if you are as ignorant of history as I was before I got pulled into this, you go, well, okay, they didn't have lenses back then. So I'm going to show you that they did. And we look at this catalog of medieval Renaissance optical manuscripts. What he means by that are textbooks in geometrical optics, dating from 1000, which is an important time when a particular Arab scientist, an Arab polymath, Ibn al-Haytham, wrote a 7-volume treatise on optics, till the time of Van Eyck. There's 61 during that. A new treatise in optical sciences, geometrical optics, was published every 7 years. They're not published that often today. So unlike what we thought, that the Renaissance, the medieval times, was a time when Cro-Magnons were fighting dinosaurs and everyone was ignorant. In fact, it was a period of intense intellectual activity. The only difficulty is that the people were kind of stupid. They didn't speak English. But if we translate Latin into modern European languages, they describe exactly how to make a concave mirror or a lens. And so I ground, another undergraduate optical experiment I do in workshops is taking a piece of aluminum grind a lens, and I ground a lens in 1 hour. And those of you from the Midwest don't know what that is. That's called a cactus. And this is the backyard. Some projectors show this better than others. There's a wrought iron fence back there. We can make out the edge of the wrought iron fence, just barely. So basically there's two categories of people. Those who don't know enough optics to understand this talk, those who know too much optics to understand this talk, who think, well, the Hubble Space Telescope, you have to correct for aberrations, or you heard Roger Angel's talk last night, you have to have microactuators take care of difficulties with density of air. The mirror that I ground was 2,000 times worse than the Hubble Space Telescope. It's a horrible mirror. It's 3 times better than Jan van Eyck would have needed to resolve any of the features in his pictures. So, begs the question, how bad of a mirror can you use? So I went to a wholesale restaurant supply company here in Tucson and bought this stamped stainless steel mirror. It's a ladle. It's got holes in it. It has multiple curvatures. You couldn't possibly, okay, here's a quiz. Could you project an image with this? Yes. Okay, so clearly a good optical scientist. Could you project a good image? Well, you can't project a really good image. Oh, sorry. So there's the scene that we're seeing. Projecting. Now, it's not the greatest image. It's totally recognizable. If you drew straight lines along the edge of that building, they would come to a vanishing point, and you, rather than Brunelleschi, would have invented the laws of geometrical perspective. So unlike what some of you think, that you need incredibly good mirrors or lenses to project images, no, you can actually have really lousy ones and have useful images projected. One of the nice things about being involved with a person as famous as David Hockney is they're interesting people contact me. I have a stalker. That's not an interesting person. I got a phone call once, not by the stalker, by somebody else, at 4 in the morning, wanting to discuss a painting. I woke up groggy and everything. And so after it became clear that there wasn't somebody making a mistake calling from Europe, I've had that happen. You know, somebody's got the time zone all screwed up. I said, you know, what time it is? They hung up on me. Well, I've got caller ID. I checked the next morning, and it was somebody from Ohio who, at 6 a.m. their time, had decided they needed to have this question answered. And I don't have a unlisted phone number. Well, this was a good one. This, I never have to remember his name because it's always right here, hidden by the bar. So sorry about that. So this professor of English called me, emailed me. He said, you're easier to find than David Hockney. Are you aware of the description of mirrors in The Romance of the Rose? Again, pleading ignorance. I'd never heard of The Romance of the Rose. So I went to the Barnes & Noble here in Tucson, and they had 2 copies on the shelf. Now, the modern publishing industry, and we kind of heard that yesterday from yesterday's plenary talk, the modern publishing industry is such that books go out of print almost instantly. That publishers publish them, and then they go out of print. So this book from circa 1200, 2 copies on the shelf. That tells you it's widely used today. And in fact, it's widely used in the humanities today. And as the introduction to the translation says, it was one of the most widely read works of the French language at the time. Well, it turns out Jan van Eyck worked as the court painter for the court of Burgundy, presumably spoke French. There are 4 pages, which you're not supposed to be able to read, that I've highlighted in white, where mirrors are discussed. And here it says, El-Azain. This is that Ibn al-Haytham, the 10th century Arab scientist, wrote the book of optics. And there you'll be able to find whatever you need to know. So he's footnoted it. And he says, in the epic poem, I'm not going to take the trouble to clarify the shapes of mirrors, tell how rays are reflected, or describe their angles. Everything is written elsewhere in a book. This strikes me as very technical language for a French epic poem. But anyway, it's a footnote. So he says, you know, deal with it. If you want to know more, here's the reference. If we magnify this, we'll see that if you're an optical scientist, he is clearly describing, for example, a mirror. If you put a bulky object in front of it, even the mountains, large mountains between France and Sardinia can be seen to be small. Sardinia is a province in the Pyrenees between France and Spain. So he's saying if you put the Pyrenees in front of this kind of mirror, they look small. That's a convex mirror, a security mirror. If you got caught shoplifting cigarettes when you were 14 in the store, it's because the clerk saw you in the security mirror. So they describe the properties of these mirrors. Because at the time in Latin, the word for mirror was the same as the word for glass. There was no separate word for convex mirror. It was just glass. It's up to you to read the text and understand that certain mirrors make phantoms appear quite alive outside the mirror, either in air or in water. Air and water don't rhyme in medieval French. They were those properties of those materials, optical properties of those materials, were of great interest to the philosophers of the time, because air, light travels forever. A solid, like the floor, light doesn't go through at all. Water is kind of funny. Sometimes it behaves more like air, sometimes it behaves more like the floor. So the philosophers are interested in that. So what I want you to do, before we knew about the Romance of the Rose, the BBC made a film about us, and David Hockney is projecting a cabbage, and it's upside down. It's hanging from a string to simulate a particular painting. That's not important. And I want you to compare how a 21st century artist describes this scene to how it's described in the Romance of the Rose.
And I realized this is a color movie. It moves. I mean, there it is. It's spinning. It's quite beautiful. Of course, it's upside down. The string's coming from the bottom. And I then realized, my God, this is a movie in color. They must have seen it 600 years ago.
They saw it 700 years ago. So what I've shown you to this point is that they could make the mirrors. They understood how to project images with the mirrors. That doesn't prove that artists used mirrors to project images. Now I have to show you that. But to do that, I'm going to remind you of some optics that you know. And I'm going to go through very quickly. Well, one thing the guys you in the Midwest know that some of us don't really know if we didn't live in the Midwest is that if you stood in the middle of train tracks, they just go on forever. And they come to a vanishing point. Parallel lines come to a vanishing point. We all know this. We learn this. But if you look at it a little more carefully, if you were standing there just before the train hits you, you go, these telephone poles are along those train tracks. They should be parallel, but they're deviations. This idea that parallel lines, if they strictly are mathematically parallel, they do come to a vanishing point. But if they're not quite parallel, they don't. And so if you look at this painting, drawn after the laws of geometrical perspective had been developed, all the facades, everything comes to a perfect vanishing points. Those of you who have ever been to Italy know the Italians can't build a city this perfect. Maybe if this was a German city, it would be. But in an Italian city, the building, we'll put a building here, put a building there. So this tells us that likely that this artist understood the laws of geometrical perspective and constructed this geometrically. This is from a widely used art history textbook. In our case, our eye is above the building. So there's vanishing points above the building at a horizon line. That's the height above the building that our eyes are. Here's a chandelier. Our eyes are below the building. And this is an optics-based chandelier. I took it with a digital camera. So they should come to a vanishing points on a vanishing line. It doesn't. What's going on here? We were taught by our professors, the students. Your professors lied to you. You're taught by your professors that all these things come to vanishing points and everything is all perfect. But when you look at a real chandelier, which presumably is good enough that people are willing to pay hundreds of dollars to buy it, that things don't work out that way. And the reason for this is if the arms are just off by 1/8 of an inch this way or that way, they look fine to the eye. Your eye mentally constructs an image that looks perfect and doesn't quite line up. This is a different chandelier. Science has to be reproducible. That's a different chandelier in a different Home Depot. I have to admit, though, both Home Depots are on Broadway Boulevard in Tucson. So but we get the same issue. So we're going to make use of that. We're going to look for things that deviate from perfection. Will be sort of circumstantial evidence that maybe optics was used. Here's David is visiting my lab. That's my MBE machine. We don't know how tall David Hockney is, but we're going to make an estimate. The average height of a European male, we look it up, 1.75 meters. That tells us the horizontal distance across the scene. At the depth into the scene which David is standing, it's 2.5 meters. We don't have to look it up. Everybody knows the length of an MBE console is 2 meters. And so we calculate the angular view of the scene, and unfortunately, cut off is the critical final bit. Again, blame Bill Gates. And it says that a 26 millimeter focal length lens was used to create that painting. My technician took our picture with a 24 millimeter focal length lens. So within the uncertainty of our estimate, it's perfect agreement, which shouldn't be surprising. It's the laws of geometrical optics. So if Van Eyck has painted a MBE machine in one of his paintings, we'll be able to use this kind of analysis to determine the focal length of the lens he used. Here's Arnold. He's going to look into the scene. He looks into the scene, and now we can see back there. Something else has changed. Now, if nothing else you get out of this talk, you'll never see a movie the same again. If we come back here, the magnification of an image, just two simple equations, all we're ever going to use. The magnification of the image, the distance to the image over the distance of the subject, and then the lens maker's equation. We can look up to see what kind of film his image was originally projected on. We're going to estimate how tall Arnold's head is. And that says the magnification of this scene is 0.06. Visualize yourself at an art museum. You're looking at a portrait. Portrait head's kind of like that. Portrait head, the magnification is more like 0.6, 10 times larger than this. The effect I'm going to show you now is much larger if the magnification is larger, and yet we can still see it here. Back of the trailer, a reflection that we can identify. If he looks halfway into the trailer, that reflection moves. Looks halfway again, or further in, the reflection moves further. The magnification of the image has changed by 8%. You didn't notice it when you saw the movie. So large effects, either that or Arnold's gaze is so powerful he shrunk the trailer out of fear. So something we're going to make use of, refocusing further into a scene reduces the magnification. I focus my lens on Masood. I change my mind. I want to focus on the clock. Counterintuitively, I want to focus on something further away. I actually have to pull the lens toward me, which the lens is now further from everybody, so the magnification of everybody decreases. It's normally a small effect. I mean, if I took your picture with my iPhone, the sensor's tiny. The magnification is tiny, so the effect is really, really small. We're talking about projecting things on large images. Again, you guys, that's called mountain. It will just kind of zoom in a little bit. We saw the mountain. It was a little bit out of focus. Now it's almost completely gone. So the other effect I'll go through really quickly. We calculate or estimate the magnification. We come up with the same number as we had before, about 0.6. Now we zoom in. Now the magnification increases by a factor of 3, but the depth of field decreased from miles to feet. Increasing the magnification decreases the depth of field of an image. We'll make use of that. When we go to large magnifications, we'll get small depths of field. And we'll just skip over this. So here's how we, proposing people like Jan van Eyck, made their images. Here's somebody dressed to look like a character in one of Jan van Eyck's painting. His image is reflected and focused by a shaving mirror on the inside of the wall, upside down, in living color. The artist captures the features that he needs to make the image look optical, and then takes it down and works on it as we've always been taught the artist worked on, from by eyeballing to fill in all the details. At that point, he's got a drawing. If he wants to make it a painting, he adds color. So here's David doing this. And watch, he'll blink his eyes. It's an image in living color, upside down. And one thing I didn't point out to you is, or maybe I did, is when you project an image with a concave mirror, the parity is not reversed. So to pick on Masood again, he has a pen in his left pocket. To me, it's to the right. If I projected his image with a concave mirror, I project it onto a canvas, I trace the parts in I want, I turn it over, the pen ends up still on my right. So I have him with the pen on my right. On the painting that I'm trying to complete, it's also on my right. That's very useful. If instead I'd projected his image with a refractive lens, when I turn it over, I turn it back, his pen moves to my left. So I've got it on his right, now it's on my left. It's still useful to me, but not as useful as a concave mirror. So at this point, this is created based on an optical projection. Oops, so Windows glitch. You can't see the Pacific Ocean from David's house in the Hollywood Hills. But through total imagination, the artist can create that. It was created during the daytime, but he can put them indoors during nighttime, or he can put them with his buddies. So all of these paintings are complex, that they're collages. Some features on some paintings were produced with the aid of lenses. That is not a weak qualification. That's actually an incredibly strong statement, that even though the paintings themselves are not effectively pictures, portions of the painting were created with optical projections. Here's a Jan van Eyck painting, very famous. This is one of the paintings that's bothered David Hockney in the National Gallery in London from the beginning of his career. How did Van Eyck make that chandelier? Well, we have a little dog there. If we magnify that dog, we can recognize it as a Bichon. Mike Knopfseger, who's not here this morning, raises Bichons, and he assures me that if you took a picture of one of his dogs with a shutter speed any slower than that, the dog would be a blur. So this tells us either Van Eyck convinced the Arnolfinis to let him kill their dog and stuff it so he could project the dog, or he had the skill to create a dog that is recognizable today. The skill to do something is without lenses is not the same as saying an artist didn't use lenses. So this shows, I would say, strong circumstantial evidence that Van Eyck had incredible skill without a lens. Shoes, he could have just kind of eyeballed those. But the chandelier, this is where a lens would have been useful. This is where the chandelier is. But even though the chandelier may have been projected in front of them, optics don't make marks. They only produce an image. Optics put images in front of the artist. The artist still has the free will. He can decide, I'm going to trace this. I'm going to alter this. I'm going to ignore this feature. And all the way through, I'm going to keep using the term, the artist, he did this. The artist, he did that. Because every artist we've been able to find so far that used optics is a male. There weren't that many female artists at the time, but in the female artists that were there, we can't find any evidence that they used optics. Very few female artists. So these are collages. So if we look at this world famous painting and we decide, is this painting based on optics? If we look here and we analyze those features, we correctly conclude that that painting is based on optics. If we only looked at that feature, we would incorrectly conclude, oh, no, the painting's not based on optics. You have to look at the right features. So here's the Arnolfini marriage. There's the mirror in the back. Now, notice where the mirror is placed. The mirror is round. If optics were used to project the image of that mirror, if the lens was down low or up high, the mirror would have been elongated. So the fact it's round, not elongated, tells us that if a lens was used, it must have been at about that height. So if we magnify it, it was about that height. So what's going on at that height? Okay, Windows. Is the man in blue Van Eyck, and the curtain behind him his camera obscura, with the bright object his concave mirror. Self-portrait. So let's see what evidence I've got that these artists actually used optics. And I'll go to, Lorenzo Lato, 75 years before Galileo. David had collected together color photocopies of all the paintings that looked to him optical, or worthy of consideration. And this is the status of the situation when I was first introduced to him. And he did it like Mendeleev putting together the periodic table. He organized things chronologically, paintings from Northern Europe on the upper wall, Southern Europe on the lower wall, looking for, does lithium have the same chemical properties as plutonium? And no, they don't, so we'll put them in different places in the periodic table. So Mendeleev put it together, David put it together this way, and one painting on my first visit, I saw this one, husband and wife, 75 years before Galileo. I realized optics had to have been used, and I'll show you the optical evidence within this painting. So we magnify that central octagonal pattern, it goes out of focus. Yeah, so what? You know, pictures go out of focus. Well, if you had never seen a projected image, you never would have simultaneously seen part of a scene in focus and part of a scene out of focus. Yeah, I don't want to keep. I'll look at Paul this time. I'm tired of looking at this. He's in focus. The clock is in focus. My brain doesn't bother telling me that going from here to there, it's caused the muscles in my eyeballs to contract, to refocus, and I construct in my head a composite, totally in focus image of everything. So I don't see part of a scene in focus, part of the scene out of focus. So there's our first bit of circumstantial evidence. Here, if you were there, you'd see the kid with the wine bottle, and you would have looked back here and you would have seen the car, and the car would have been in focus to you, not out of focus. There's a set of vanishing lines in the front, another set further back, and I'm going to show you a third set in a moment. If I put this back, well, if I try to correct for perspective, it sort of doesn't matter what I do. I try all sorts of things. That's too large, that's too small. I can't correct for perspective, which seems at first glance, you know, if I'm telling you that you used optics and I'm saying you can't correct for perspective, I don't know what that means, and I'll show you what that means. If I put this back in, it goes out of focus somewhere back in here. If I look over at a different part of the painting and I magnify it, there's a set of vanishing lines in the front, a set of vanishing lines in the back, and they differ by 3 degrees. Well, then there's other stuff I'm not going to talk about today. I'll try to reproduce this. What I'll do is I will put a camera on a tripod, aim it at a geometrical pattern on a bedspread, and I'll take a photograph. And then the only thing I'm allowed to do, I'm rigidly locked on the tripod, is to move the lens in and out to focus further or back and forth. And I'll composite together the back of this photograph, the back of that photograph, and then I've got a composite. Looks fine, but if we look at it more carefully, the ruler is kinked, and it's kinked by 3 degrees. Every feature that we've shown is based on optics, we've reproduced optically. Okay, well, I've told you I can't correct for perspective, but I'm going to try again anyway. And there's a length scale. I've created this according to the size of of these carpets that we know existed, and I'm not really going to use that right now. So I'll try to correct for perspective, I'll get rid of the ruler, and I'll put this in color, and I'll lay it on top of the painting. Now, every scientist has been in this position. I'm sure Poole has been in this position. He's taken lots of data. He's got some curve that looks like this. And the conference he's got to leave for in the morning. What's he going to do? So he goes to the conference and he says, I want to draw your attention to the perfect agreement we get with our data. And, and then somebody in the audience goes, what are you talking about? It disagrees completely. But Poole's a smart guy. He says, this isn't what Lato would have seen. He would have seen, if you project an image at large magnification, I've had to simulate this with Photoshop, this is totally out of focus back there because of the depth of field is so small. So what you do is you fill in the part that is in focus, and now you refocus. You pull the lens toward the canvas, the magnification decreases. Well, it doesn't fit here, but it doesn't matter because you've already painted that in. Now you fill this in, refocus a second time, and you do that, and everything agrees. to a couple of millimeters, as good as a handmade carpet could be. There's a length scale in here. The distance across the woman's shoulders is 10 inches. The distance across a real woman's shoulders is 18 inches. I know that because I have a wife and 2 daughters. So I have 3 data points. In the land of the dataless, the man with 3 data points is king. It's more data points than existed in all of art history up until that point. So the magnification is rather large, 0.56. That means the depth of field is small. What that means is, since this goes out of focus somewhere between 5 and 9 repeats in, and since there's a nice geometrical pattern, it means that I now know the depth of field in real units of centimeters. So I don't have to make up anything up. And in fact, I can't make anything up. I have my 2 equations of geometrical optics. I have the magnification in the front that I just measured, the depth of field I calculate. So I've got 6 equations and 7 unknowns. What does that mean? It's like 9 o'clock in the morning. 6 equations, 7 unknowns.
This is it. That moment they told us about in high school where one day algebra would save our lives.
Now you should see audiences that are not scientists. When I say 6 equations, 7 unknowns, it's just terror comes across the face of much of the audience. So this means if I make one assumption, everything else follows. So I'm going to assume the distance from the lens to the carpet was about 4 feet, basically to the front row. Couldn't be 12 feet. That would be unrealistic. It couldn't be 3 inches. So I make some estimate. I put numbers on it. And if I do that, everything follows from there. All the depths of fields, all the magnifications. So geometrical optics dictates that if actually Lorenzo Lotto used a lens, there have to be 3 regions and 3 sets of vanishing points. And there's my initial fit. The distance from there to there I'll call D1. After refocusing, that decreases by 13.1%, measured. I calculate it should have decreased by 12.6%. It agrees to 0.5% accuracy. Very few of us do experiments to an accuracy of 0.5%. We don't need to in order to demonstrate some phenomena has existed. And it agrees to 0.5%. Refocus back here. It changes by a different amount, but we calculated a different amount, and it still agrees with 0.5%. An important feature, early on people are always having trouble confused with this, and this psychologist did a nice job saying, we're not saying that perspective is the only way to get, lens is the only way to get perspective right. We're saying that lens is the only way to get perspective wrong, and precisely to 0.5%, these artists got the perspective wrong, if you will. It's because they had to refocus. Something else developed recently, I've made a high-resolution infrared camera. So here I've taken a picture of a red blotch with my regular camera mounted on a tripod. I'll take the regular camera off, put the infrared camera on, and take the same picture. And we see that underneath the red blob, I had written underdrawing. So a film crew flew me to St. Petersburg to the Hermitage. There is husband and wife right there. And with my infrared camera, I'm taking a picture of that. We'll see if we can reveal anything. It's really easy to see in the infrared. It shows up beautifully. Here is that painting in the visible. There's a lot of stuff I could talk about. I just want to draw your attention to just one thing. He's wearing a black smock. She's got a black smock on her. In the infrared, her black is different than his black. And there's other stuff, a lot of things going on there, which we haven't got time to go into, so I'll just skip ahead. This is what that triangular pattern, or that octagonal pattern looks like in the infrared. Everything takes place in a distance of a couple, like less than the width of a 3x5 card. So imagine the artist drawing within the width of a 3x5 card. Here is the same region I showed you in blue before. If I magnify that as big as I can make it to fit everything else on there, take away the stuff we're not going to pay attention to, it looks traced. The middle region abruptly changes to all messed up. Looks like he's getting back on a roll. He refocuses again, and he gives up. So in 3 regions, we see exactly what happens. If you have a geometrical pattern and you change it by 13%, you can't match it. It doesn't match. So you have to struggle. And I'm going to run out of time. Let me just skip over this. There's a lot more in this painting. So here's a video a master student made, John Shattuck. This is the painting to real, or to life size, one lens of a pair of spectacles. He's going to focus that image. Oop, didn't play. Focus that on a piece of transparent plastic, and he's going to paint it. And when he's all done, he's going to put it at life size onto a life-size copy of the painting. So here's the region closest to him, again using the same color as blue. He'll jump ahead and finish the blue region on transparent plastic, and then refocus. But has to pull the lens toward him, decreases the magnification. There's the intermediate region, which you can see come into focus now. He'll do the intermediate region, jump ahead and finish that, and then do a second refocusing. And then when he's all done, he'll take this transparent plastic, and on a life-size 1-to-1 reproduction of the painting, we'll see if it fits. And it's perfect. This is how Lotto did it. Go to art-optics.com. Let me just skip over this. And I'm going to skip through this one because I'm out of time. And I'm going to jump to a final. Go. One final example. This is now another example where things fit. And John reproduced this also perfectly. The last thing I'm going to show you is quickly an anamorphic image, Hans Holbein. This painting, in fact, is larger than that screen. It's a very large. It's 6 foot by 6 foot. There's a whole bunch of stuff going on. If we take that globe, oh, Windows, I hate you. If we rotate the globe right side up, we see Sicily is in 5-point font. Your computer doesn't give you 5-point font because you can't read that. It's too small. Every square inch of a painting that's 6 foot by 6 foot is covered with that kind of resolution. We put that back. What is this? If you could stand up and look at this at grazing angle, you would see it's a skull. But it's a bad skull. Art historians are impressed by how good a skull it is, that in fact it's a skull at all, and it's like it's a bad skull. I'm going to tell you why optics made it a bad skull. If we take that skull, linearly compress it, it looks like this. If I took that skull and I put it next to a real skull, jaws too long, bulge back here, and a sinister right eye. When you guys were a little bit younger, when you were trick-or-treating, if you're going through a house and your parents were going trick-or-treating with you, if they saw a skull like that on the front porch of a house, they said, let's go to the next house. There are ways to make an anamorphic skull graphically. You could put a grid pattern on this skull, lay out a non-linear grid pattern, do a 1-to-1 plot. But the feature of this is, if you decide to go back, you get back what you started with, subject to any errors you made in the transcription. I'm going to show you that's not what we get. There's a skull. There's a concave mirror. We're going to project it at a grazing angle to make it anamorphic. So a circle ends up being an ellipse. It gets spread out. I'll take a picture and I'll show you the anamorphic skull. When I'm all done, I took the mirror out. This is what the skull, what the mirror thought the skull looked like. This is what you'd think you'd get back. So when we do this, though, depth of field. It's a blur. The jaw is in focus. Well, let's paint the jaw in. At this point, our canvas is the jaw painted in and everything else is blank. Move the concave mirror, refocus. Well, now the jaw is out of focus, but we'll paint in the teeth. It's in focus. And in this way, we'll piece it together. And we get an anamorphic skull. I'll put it on a line. Now I'll linearly compress it. And it doesn't look right. The jaw is too long, bulge back here, and that sinister right eye. We've seen that before. And we can even see something else where he screwed up. It was a real easy mistake to make. He duplicated a particular segment. He should have painted that if he hadn't made that mistake. So we can see a mistake that he made. The magnification is linear in this direction, goes as 1 over sine of the grazing angle in that direction, and it's piecewise segmented. So an alternative explanation is that Hulman knew how to solve a piecewise segmented nonlinear transformation, and he did its plot that way. And so, to summarize, I've only shown you a piece of overwhelming scientific evidence in images that optics was used. They are not photographs, though. They're much more complex than that. Optics don't make marks. You have to look to see where the artist had deliberately made changes. We can have insight into, we can actually answer questions, thanks to optics, that people didn't even know they could ask before. That if you can show that a painting is based on optics, and you can show that the projection is altered from what the artist actually would have seen, that's an aesthetic choice that somebody like Caravaggio or Van Eyck actually made. And we can understand things. It does fundamentally affect our understanding of the evolution of art the past 600 years. That sudden dramatic transformation to realism was seen before. Nobody understood why. And a variety of applications to optics and photography and the like. That people, sorry for you professors, that people who are not scientists really don't care what you're teaching them in the introductory optics that they've got to take. But if you say, if you pay attention, I'm going to teach you something that's going to let you understand this beautiful painting by Jan van Eyck, and put yourself in his shoes, they're going to pay attention to you.
Here's what's so revolutionary about what you're saying. You're saying the history of art, the history of the Renaissance, is the history of optics.
I am saying
I know that,
yeah.
and you're blowing everything up. You're blowing everything that all of us who took art appreciation studied, all the art historians have written, and you're saying you're all wrong. It's all about optics.
Art historians haven't responded well to that. You've had a paradigm shift. So thank you for your attention, and sorry I went a little bit long. Now we're probably running late, so I'm happy to answer questions at the break, depending upon the chairman.
Let's take a couple of questions.
Yes.
I'm thinking about your table clock example. I'm imagining if I took data in the lab and I've got all my data points, if I wanted to say I'm going to fit it using 3 different equations, one equation to fit here, one equation to fit here, one equation to fit here, it seems like if I'm composing multiple fit equations, I could fit pretty much any shape I wanted.
Yeah,
so I'm curious about if you were to just draw any old version of the hexagon, could you use that same series? Because it just seems like there are a lot of free parameters. How many times you refocus? Where do you focus?
No, there's only actually the one free parameter. You really do end up with 6 equations and 7 unknowns. That you have the because of the depth of field. If you impose a hexagonal measure on it, and you use the wife to determine the magnification, that tells you the depth of field. You don't get to mess with that. I mean, you've got the depth of field from the magnification, and then you end up with the 6 equations and 7 unknowns. You've got the one free parameter.
I guess what it seems like free parameters is how many times you refocus and at what point you're moving the lens to.
The depth of field tells you when you have to. I mean, again, you're back to the depth of field. I'm saying when you exceed the depth of field, you got to refocus.
Question?
Everything you say is very compelling, but we're not art historians. We haven't looked at the counterexamples. We don't know any context for the contemporary technology of those times. So to me, knowing that there are critics of your proposal and not really having enough first-hand exposure to distinguish, what would make it most compelling is there any documentary evidence, any journal from an artist, an apprentice, a collaborator who helped grind lenses, some sort of direct statement in support of this hypothesis?
Okay, so that's a question that's often answered, often asked, and there are no documentation of Van Eyck's at all, of anything He doesn't tell you what his grocery list for the day is. Say that the evidence is in the images. So you have to understand the images. The images tell you everything. If Van Eyck had written, under no circumstances did I ever use a lens in creating these paintings, I would say he lied. So the written documentation, which is what art historians base this on, are that's all they've got. And there is no documentation one way or the other at the time. I would say the other thing is, if you understand the documentation, the images, they tell you. I've had an art historian, when I show 6 equations and 7 unknowns and solve for all this, say, well, that's your explanation, that's your story, I'm sure there are others. Well, no, there's not. I mean, algebra, there is not another story to algebra. But in direct answer to your question, no, there's no writing one way or the other at the time. Yes?
One very quick one.
So last year I saw a documentary from Penn and Teller, and unfortunately I missed your commentary on that, but it was an alternative where I think they used a flat mirror and basically held it over the painting and were able just to paint over the edges up to that mirror or something like that. Could you just comment on that theory as well?
Yeah, so in fact it was a lens that he had a lens and a mirror involved in that. And that is, oh God, what was the name of that? Something Vermeer. Tim's Vermeer. It was the movie. And so he actually had a little bit more complicated optical arrangement. And in that, how many of you have seen that movie, Tim's Vermeer? Just a few of you. In there, David Hockney appeared, and they asked him what he thought of the painting. And I know David Hockney. He's very polite, and he wasn't thrilled with the look of that painting. That painting looks like a paint-by-numbers painting when you're done. It doesn't look like a Vermeer painting. But it is an optical projection. And it just shows you, with an optical projection, you can produce, anybody, even me, could produce a paint-by-numbers painting. But it doesn't, an artist makes something that's beyond that. Okay, thank you.
And our next speaker is Robert Bunch from Hulman Institute of Technology, and he's going to tell us about their optical engineering senior capstone design and curriculum and how that has evolved.
Okay. Sorry about that. It was clearly a session German's.
I think so. I think so. I had to get my computer ready anyway. Well, good morning, everybody. Design experiences for engineering students are an essential component of their education. But teaching design is a really hard thing to do. And after years of trying it, I can tell you, I think we have some ideas, and that's what I want to try to present to you today. So in this talk, what I'm going to do is focus on our Capstone design course for optical engineering majors at Rose-Hulman and how that's changed a little bit over time. And so here's what I'll do. I want to give you a little bit of an introduction about my school because it's well known in the optics community, but sometimes not so well known in some other places. And there's some interesting facts about the place. Talk about our engineering program in general, as a general overview, and some of the curriculum and organization. And part of that has been driven by ABET accreditation and some of the updates in ABET that have occurred, and we've made some alterations of our programs in response to that. But I'll really focus on the design course. It's a design course sequence, and talk about how that's changed over time, how we select projects for the course, And these are capstone courses and often called senior design courses. And I'll give you some example projects and then summarize the results of that. If you look at the map, you can see that we're located in Terre Haute, Indiana, in basically a triangle between Chicago, St. Louis, and Cincinnati, about 60 miles from Indianapolis. The school is a private college of engineering, science, engineering, and mathematics. We only have those technical majors. It was founded in 1874 and named Rose Polytechnic Institute. Chauncey Rose was the founder. He was a railroad industrialist, interested in having people work on his railroads. So that's what the engineers do. In 1971, it was renamed Rose Hulman Institute of Technology in recognition of the Hulman family, who took their whole entire foundation and donated it to our endowment. Hulman and Company is still in operation. They are the manufacturers and sellers of Clabber Girl baking powder, but they're probably most well known as the owners and operators of the Indianapolis 500 Motor Speedway. So that's we have a good connection to the Speedway. In fact, our commencement is always based on whenever the Indy 500 is. We're a pretty small school, 2,200 undergraduate students. We have a small master's program in many of the engineering disciplines. A selective school. Our freshman class this year was 547 out of about 4,000 applications selected. 180 full-time faculty, average class size of about 20. One of the things that's interesting here is our optics educational programs began in 1983, so we've been having optics education for quite a long time, particularly at the undergraduate level, primarily at the undergraduate level. We're recognized by a number of places. Brookings Institution was a recent one that was a nice one. I want to highlight the Princeton Review because we were listed in a number of categories in how they rank 380 colleges. Best career placement is nice. Colleges that pay you back, number 8 is nice. But students study the most, number 18. We need to get that up a little bit. So we'll work on that. As I said, our optical engineering program is in place. We've been teaching optics, but it became optical engineering in about 2000, and that was in response to some changes in accreditation processes that ABET followed. We have strong ties to the societies. We have a number of good educational labs, a number of well-equipped specialized labs where we can do research projects and design projects that that I'll talk about primarily here. Let me say a little bit about accreditation because that's what drives a lot of engineering programs. Particularly, this is a new criteria that specifically identifies and called out that all new accredited programs in optics, optical, or photonic assembly name programs will have to meet. And the thing I want to highlight here is what's called out is that the curriculum must prepare students with appropriate knowledge and lab experience in these areas: geometrical optics, physical optics, optical materials, and optical or photonic devices and systems. So those are must elements that have to be in any program. In addition, the group that put this together, I wasn't involved in this, but the group primarily from SPIE who put this together listed also that faculty who teach significant design courses have to be qualified with a virtue of having design experience as well as subject matter, which is really even more strict than some of the more traditional engineering programs. So this is what needs to be met from now on for any program that is accredited. ABET also says about design that's in a couple of places that student outcomes in the student outcomes area under ABET C, students must be able to design a system or component or process to meet desired needs within realistic constraints. This is very engineering, and these constraints can be a lot of things. But also in the general criteria, students must be prepared for engineering practice through through a major design experience. This is often called the Capstone design experience or senior design in engineering programs. And so this is really what I'm going to address mostly in my talk today. But I want to give you an overview of our overall curriculum, because what we have done here recently is reorganized some of the coursework along these tracks that ABET have identified. And we didn't really make a lot of changes. I just reformatted this and put this in the table. But it does well describe our approach to curriculum design. In the beginning year, freshman year, students take our introductory physics and physics classes, and in physics, our Physics 3 class contains Introduction to Geometrical and Physical Optics, so it's listed in that area. We also have a small survey course that involves lasers and fiber optics, and so that is in the Devices and Systems area. Students take Introduction to Engineering Design. Freshman design is what it's called. In the sophomore year, that's when the students begin their foundation program, geometrical optics, physical optics, and photonic devices and systems. Those are 3 different classes. We're on the quarter system, and so each of these are separate classes. By the way, I put a little designation here. Wherever it says L behind it, that designates that course has a lab associated with it. So we have a very intensive lab program in the program. And in year 3 and 4 is where we begin providing depth and breadth in the areas of optics. And so you can see that fiber optics, lasers. But from the design perspective, in the year 3, the end of the student's junior year, is when we begin our optical design sequence. And we do that purposely, and I'll get into the reason why later on. And then in the senior year, we have two courses that follow along in sequence where they do their actual capstone design project. I've also, in gray out area, are some of the elective courses that the students can take as well that are available to them. They have to take a certain number of elective courses. So to set the stage then for design courses, we've had a kind of a project course for a number of years. There used to be called Applied Optics. It was a nice course. We combined juniors and seniors in one class, and we took them through a small, very directed project in 1 quarter. That worked very well for its purposes, but when we became optical engineering, we had to have a capstone design. So in 2000-2001, we started this optical engineering capstone design. We took those 2 quarters and put them into 2 terms in the senior year. It was a complete failure. It was. One good thing about design is one of the mantras of design is fail early and fail often, and that's what we've done here. So we've practiced design as we've put the curriculum together. It was a failure because it was a nice project, but the students got into the course and they really weren't prepared for this class. They're supposed to be working in teams. Well, get together and work in teams. You know how to do that. No, they don't. We haven't given them instruction. They needed more time. So the first fix was we said, okay, the next year we'll make this 3 quarters long. If 2 quarters doesn't work, let's make 3 quarters. Let's make it a full year. That didn't work either. That failed. And here's why. This is really a paradigm shift in the way the students are expected to learn. They go into classes, they do labs. Even if some of the labs have projects related to them, they don't usually work in teams. They're not ready for this. They've got to understand the design process to do design. And they lose perspective about what the design process is. When you do a project, you got to focus on something. You forget the thing as a whole, which is what you've got to always keep in mind when you're doing a design project. So, fortunately, there's a lot of educational engineering educational literature around. And this group, Marin, did a great survey of a number of programs and came up with elements of an optimal capstone design experience in the Journal of Engineering Education with full assessment. And they describe 3 elements that are needed for a course like this: student preparation, project selection, and instructor mentorship. And in student preparation, what they talk about is exactly what we discovered. Students have to crawl and walk and run. It's just like an infant. You got to learn to crawl before you can walk, and so that's where we are. Not that the students are infants, but in design, maybe. You have to have sufficient coursework preparation, and you have to be able to take elements that have been integrated previously. The students, faculty, and industry have to see the project as worthwhile, and so you have to select projects that everyone is interested in and wants to be working on. Now, not everybody's interested in all the aspects of this, but it has to be an element. And instructor mentorship. And one of the main elements here is the mentor doesn't lead the team. So as a faculty mentor, I don't lead the team. I'm there to provide as a consultant, but the student team is what's working on the project. And we need to provide them the tools to give them success. But as I put down there, failure is an option. Although I don't think we've had to fire students from teams. We've never had to fail a student from a team. So here's how we organized this. We took our spring quarter course, as I said, that we have in the junior year of this, in the spring quarter of the junior year, and we use that as a course focused on product development. There they learn some of these tools that you need to do and work as a team in an engineering environment. Things like concept generation and concept selection and being able to select down from a variety of potential solutions. We give them some teaming exercises in this case, and this is done and I'll show you in a minute, in a mini project-oriented laboratory environment. When you get into the next fall and winter, that's when they start their main capstone project work. We also give them some tools to do that. Those are the things in black there. And then the items in red are the content that we require, that are covered and we require. It's a highly deliverables-oriented approach. So there's a prototype, there's final reports, final presentations, design reviews along the way. So here's how we do that first course. We teach the design process through a set of mini projects. We've taken these, and this is the learning to. They've crawled by taking our courses previous to this, and now they're going to learn to walk and do projects and do design projects. So we give some simple, more straightforward projects, and we've identified in various areas and kind of put them and classed them as a discipline. So in the mechanical design, we give them, and in this case it's done in a couple of ways, but in this particular illustration, we give them an optical component and they have to design a mechanical holder for that or some kind of mount and have it rapid prototyped and show that it will hold the component. We give an electrical circuit, and here's an example of one of those, or we just give an idea and the students then come up with a design, build a night light. And so it has to turn an LED on when a detector is covered. And so they put that together and build that system. This is in about a week and a half. We give them a big block of aluminum and a heater and say, design a heat sink that's going to sink the mass of the thermal output of the heater. And they have to go into the machine shop and machine off to get enough fins, to give enough area to get the cooling done properly. And these are then also, they have to match a set of bolt holes where they're bolted onto a water-cooled base. And we also do then an imaging system design, which is shown here in the bottom right. And they build a prototype that is a lens in front of some kind of camera. We've used standard cameras from Thor Labs as well as just webcams in the past. We give a little kit, and again, these are idea-oriented designs, so the students have to put some information into developing the specifications themselves. We put this little kit together from 2-inch Thorlabs components. We give them a set of lenses. Part of the constraints here is that they have to use these lenses. They're commercial off the shelf. Some of them know the specifications of the lenses. Some of the lenses are unknown, so they have to make measurements of those. And they can, and in fact, the best designs come from the ones that they have to make measurements from by design, by our design. And this, what student called this, one of our former students called this the grade cam. We put this page 20 feet away from where their lens has to be, and you can't read it probably, but it says, if you can, at the top line it says, if you can clearly read this entire line on the screen, you get an A. So it's an easy, quick way to say whether or not they've achieved the goal, and they in fact do. See, you can see here, if you can clearly read this entire line on the screen, you get an A. And they also learned something because they did the specification right so that they got the entire field of view along the diagonal. So this was a good case. Of course, we have students, I'm happy to get a B. They'll put one lens in front and image it. I got a B. Okay. But this is also prototyped at the same time. The tools of design we teach through some activities. Here's one example. We teach design of experiments. We found many times the Capstone projects require some kind of design of experiments. You've got multiple factors that are involved, and a nice little fun thing to do is to fly helicopters. So they cut helicopters out, and there's 4 different parameters that can be involved here, and they all interact with one another. Wing length, wing width, body width, and they drop the helicopters and let them twirl around and fly, and we try to maximize the time of flight. And so by picking the factors, then they can use the factorial methods and pick the factors that optimize the flight, and then they make the plane or the helicopter that matches that and drop it to see whether that actually does optimize the time of flight. So a lot of projects need this, so we use this as an example. Project selection is the second criteria, and these have to be challenging, they have to be doable, they have to have many solutions. We're not picking one particular solution. We don't want to prescribe one solution. That's not design. You have to have multiple solutions possible. It has to be doable, but not necessarily obvious. We also require that these, in our selection, we need a hardware deliverable. That's an important element that we've identified we want. It has to be a component device. Could be a breadboard. Often the clients want us to ship the end product to them. We do that occasionally, not all the time, but we do that occasionally. And it's got to be of interest. And what this has led us to, all of these criteria have led us to picking client-sponsored projects, and so we've focused on those in particular. Here's how we go about that. We want to begin in September in our fall quarter with the Capstone course. So in March, the faculty members start soliciting projects from companies we've worked with in the past. We do consulting work. We have projects with where we talk to former students and try to get projects from them. In June, we have them give us a brief overview of the project. We vet those in July, pick the projects and finalize them. And then in September, we give the students a preference, and they pick a couple of preference projects they want to have. But we form the teams, and we do that on purpose because you have to make sure you form teams properly. And we also base that some on the peer evaluations because the students in the previous course have worked together. And so we have a little bit of information about who works well together and who does not work well together, probably more importantly. And then we do a face-to-face meeting or a teleconference with the clients. So these Capstone projects are generally industry-sponsored. They're 20-week duration. It's deliverable oriented. We have design reviews and milestones that the students meet. They develop the schedule like any design team would. We have their demonstration set to the specifications that the students have also developed. And we hold them accountable. And that's the next part of this major, of the Marin study, was that instructor mentorship plays a role. And here's how we do that. We use a quad chart in a weekly meeting with each team. So the faculty meets with each team, and they have to show us their project plan and how they're following along the schedule, what they accomplished last week, what they're planned to accomplish this week, and what the risks and issues are. And that's how we assess those every week. Of course, nothing ever falls along the plan you identify, and so you have to put in some mechanism to change. So we institute, there's really a formal change and specification process that has to be developed. I've listed it all here. I'm not going to read it all to you. But as you see, it's a number of things there that make it painful enough that you don't want to make too many changes along the way through the project. But we can hold teams accountable for this, and it also helps discourage scope creep, and it helps discourage scope creep by the client as well, because that happens quite often. So I want to show you a couple of examples. I've got 3 examples of projects from 3 different years. Here's one we did with Valeo Sylvania. They're now Valeo International. The Sylvania pulled out of that place. It's in their North American headquarters are actually in Indiana. They do automotive lighting, forward and rear projection lighting, no interior lighting. They had a problem where they were injection molding plastic waveguides, and they had a number of defects in the plastic waveguides, so they wanted a machine to be able to measure those defects, and so they gave it to our student team. You can see the little waveguides there that are there. It's like what you see around a headlight that may be a daytime running light. And these are driven by about 3 LEDs, I think. So they designed this little device over here. You see the rendering of it from SolidWorks, and then you can see it in real life behind there, all lit up behind the students in the picture. They used an imaging-based approach and then had a number of good parts and bad parts supplied by the client, and they did the statistics on the image profiles of the illumination they would see and found out what image profile gave a good and bad headlight, wrote a GUI in MATLAB to collect the images and do the analysis right there, and it turns green if it's good, if it turns red if it's bad. This was also one of the interesting things about this development is the students did a good job of pulling information from their client, because they found out this was going to also be used in Mexico at one of their plants, and so they actually made the GUI bilingual. So you can click down there and it'll speak Spanish to you, or at least it'll be written in Spanish. So it's a nice feature. Here's another project example from DLOS. They wanted to have a system that aligned volume Bragg gratings to lasers in an automated way. And so the students have a couple of, you can see the little prototype here on the bench. There's a couple of motion controllers. You put the volume Bragg grating in, and you watch the OSA, and this will move around and collect information, and it works its way back to where you get the optimal laser output, and so you get one output for the laser, one output of the laser there. This was a LabVIEW based system that they had to use for this situation. And here's another one from, was that 2 years ago? Yeah. And this teradiode, this was, they wanted a tool to show from the diode manufacturer's point of view, what the mode structure of some of their diode systems were. And so this is the layout that the students designed for a mode spectrometer on a camera, and you can see there's some of the theory for the diode bars, and there's the image capture of the measurement. So this was an early photo, not the final result, but an early photo showing they were going in the right direction. This student group actually took this, packed this device up, took it to an international show in Korea, and student design in Korea, and won a prize. So it was a nice feature of the project. So they packed the whole thing up and put it in a box and took it overseas. So in summary, for a really optimal design course, there's student preparation, project selection, and instructor mentorship, and all of these are important. But I think it's important from the student preparation, because I think this is more global than just design. You have to really have students go through the crawl, walk, run process, and we hope that they've had sufficient course preparation in the crawling, and in walking we give them those mini projects to get them used to doing design projects, and they're ready to run with the client-sponsored projects. And I think you have to also hope that there's going to be frequent communication with the client. You can't guarantee it, so we try to fill that in with some mentorship directly, and focus on accountability is one of the issues, and I think that helps a lot with making sure that these kind of projects stay on track. Thank you.
Questions?
So your program interdisciplinary, or is it only the optics engineers that work on these projects?
Oh, yeah, good question. We also have engineering physics in my department, and so we combine optical engineering and engineering physics. I forgot to say that. And so we actually, it's kind of nice because we have a mix of student teams. Occasionally, we have had someone from electrical engineering, some students from electrical engineering also on the projects in the past. Yeah.
What fraction of your master's students are from Hulman, the undergraduate?
Oh, not very many. A few. We get a few. We have a small master's program, so it's about 12 students at any one time over a 2-year period. So we might have 2 or 3. We don't get a lot. We get mostly new students. We have a dual program with Seoul Tech in South Korea, and so we have an exchange program with there. So we do have some of our students stay in that program and go to South Korea, and then come back and do their thesis work. Yeah.
How the students work with each other, how well they work with each other, is that part of their grade?
Yes.
Okay, so how do you decide that?
It's those weekly meetings with faculty deal with that. We also have 2 rounds of peer evaluations, and so we get an idea from that, and we use those as part of their final assessment.
Do your clients fund their projects?
Yeah, they're funded, some more than others, but often if, in building that last device like I showed, that was all the components and parts and everything were bought by the client company, and then we deliver those.
Okay, in the interest of not using up our entire break isn't just yet, by the way. But let's cut it off here, and you can continue discussions with Professor Brunch outside during the break. And we'll switch to the next speaker. And so the next speaker is Alex Small from Polytechnic University in Pomona.
It's my screensaver. It should be. Wait. Why is it giving you my screensaver instead of? Okay, there we go.
Here you go.
Oh, right. Right. Put this here. Okay, can you hear me on the, is it coming through on there? What? Oh, it fell down. I'm such a loudmouth, I usually never get mics. Usually they want to take a mic away from me, so. What? Okay. Oh, and I'm on video too. Okay, I can. Oh, it's almost like having a mirror, so I can. Well, it's a pretty distant mirror. Okay, is this showing? Is this coming through on the mic? On the. All right, I'm Alex Small. I'm at Cal Poly Pomona, which is the same institution as Ertan Salik, who spoke yesterday. And I'm also involved in the local OSA chapter, which I'm mentioning for two reasons. One is, of course, to put in a plug. We have a number of Arizona alumni in the Optical Society of Southern California, and we always love visitors. So if you are ever in the Southern California area on the second Wednesday of a month, please do stop by one of our meetings. We would love to see you. And also, it's very relevant to a lot of what I'm going to talk about today, because what I'm going to be talking about today is changes at least in the first half, changes I've made in my optics class in response to being involved in an organization where most of the people are scientists and engineers from industry rather than fellow academic scientists and engineers. So I'm going to start by talking about how I brought ray tracing into my optics class. A rather succinct model of light, one that works quite nicely for most of what we do, is to divide between wave and particle behavior. Now, this is admittedly an artificial distinction, as the last speaker yesterday pointed out. Light is light. It does what it does, but we often distill out one or the other aspects of its behavior for simpler understanding. So if we think in terms of those two limiting regimes of behavior, in one you're doing physical optics, you're using Maxwell's equations, it emerges in a very distinct range of variables. You have to have a large number of photons. You have to have path differences comparable to the wavelength of light so you can get interference. And the other one, you're only going to really have good evidence for photons if you have a small enough intensity so that you can detect distinct counts in your detector. But really, although people talk about wave-particle debates in the early history of optics, that particle model of light was based on the propagation of light. It was concerned with, does light go in a straight line or does it spread out? And wave-particle duality in quantum mechanics is very different. You're talking about whether light is a continuous field, where the electric field could have any value, the energy could have any value, or is the energy coming in discrete clumps? And so although we refer to both of the middle and the right regime as particle behavior, you understand them very differently mathematically. You apply them to very different questions, propagation versus detection. So we don't have duality, we have a trinity. Now, geometrical optics, ray optics, in physics departments is usually considered boring. It's old, it's mathematically elegant when you get into the principle of least time, but it's old. So here's what I got in my classes, and here's what you would find in a lot of the textbooks still used by physicists, not to be confused with optical engineers. You get Snell's law, you get the law of reflection, you get the principle of least time, you get the thin lens equation. We do some calculations by hand. Aberrations exist. You learn that there's a taxonomy for them. We don't usually get too far into them. At some point, somebody writes down a Taylor series to third order, says, look, each of these terms represents something in this zoology of aberrations. We'll do something really advanced now, matrix optics. Now let's get to the fun. The problem, as I quickly learned from getting involved with people in industry, is that geometrical optics may be old to physicists, but it matters a lot, and they don't just do thin lens equations. Aberrations matter. They don't do a lot of hand calculations. They only do them as starting points, not ending points. They use software, which can do much more precise calculations, much more accurate calculations. They're using very flawed lenses and mirrors, and it's not enough for them to say, yeah, aberrations exist. They have to know, did they choose the right lens? Did they choose the right curved mirror? So the question is, what should I do? Should I teach aberration theory? Should I teach optical design? Well, the truth is that the classical aberration theory, lots and lots of Buchdahl coefficients and everything, it's confusing for a lot of students, and if you get too far into it, some of it's still confusing for me. Should I teach optical design? That's not really where my strength is. Design is not my bread and butter. The previous speaker pointed out that there is a reason why design should be taught by people who have done a lot of it, not just simply anyone who says, yeah, I know some optics, so I clearly understand it. Oh, well, the light went there, and this is going to detect that. There's a lot more to design than that. But can I use software to at least teach the fundamentals in a more realistic way? And the answer to that is yes. So we started with Oslo. It's free, but it's not popular in industry. Now we're using ZMAX. It's a lot more popular. It has a nicer interface. There is an educational license that's very, very cheap. But I can only use it for the academic term that I'm teaching optics, so I can't pull up ZMAX today. They took away my license as soon as I gave my final exam in December. Here's why it matters. Let's start with a homework problem from one of the classic optics textbooks, Pedrati Cubed, because it's written by three people named Pedrati, a father, a son, and an uncle. And they just specify a plano-convex lens. They give you the refractive index. They give you the radius of curvature for the non-flat side. And they tell you it's going to produce a 4x magnification. But let's say we put that into ZMAX. And so we set that up, and we're going to set it up with a really small numerical aperture. All right? And we're just going to send rays through that. All that ZMAX does is it takes the rays and it sends them through the lens. It doesn't say, oh, 1 over S1 plus 1 over S2 equals 1 over F. It just says, well, I've got a ray that hit the lens here where it's curved, and you're thinking you can't see anything on here. He's giving a really bad presentation. Well, I'm doing it for a reason. I'm drawing it this small because the result is already bad. You can imagine how much worse the result would be if I had a larger numerical aperture. It just says it hits something curved here. It uses Snell's law, figures out where the rays are going to go, and brings all the rays together over here. Now let's zoom in on the spot diagram. Just look at where all of those rays hit in the image plane. So here's a sample of the rays. And what I want you to notice is that the area radius, the most basic resolution limit calculation says, oh, well, a lens with middle of the optical range, imaging with light in the middle of the optical range, and using a lens with that numerical aperture should form a spot that's about 16 microns wide, except it's really 204 microns wide. If the goal of that problem is simply to say, can you do a calculation using the thin lens equation and the lens maker's equation, the answer is yes. If the goal of that problem is to show you a lens that you want to use, not so sure about that. So what do I do instead? I still give them a few lens maker equation problems at some point. I try to run them through Zmax before I do that so I can make sure I'm not giving them the most atrocious lens possible. But then I can move on to questions like, which of these 4 lens pairs should we use? The lens maker's equation would tell you that they all have the same focal length. So what's the big deal here? Well, the big deal is that if you actually run them through a ray tracing program, you find out that for aberrations, the orientations matter a lot. And so I can just give them an assignment where I say, run it through there, see which one is best, and then try to understand why. Try to use the fact that paraxial optics works best when n sine theta is small. And for a given magnification, when is n sine theta the largest or the smallest when it hits each of those surfaces? So here's some example output. Here's what you would actually get. You get that zoology of aberrations illustrated through something that's a little more thought-provoking than a Taylor series. You could actually play with it and test it. You could figure out what are the trade-offs. If I had a situation where I needed a given resolution, what am I going to get? Is this acceptable or not? We can do point spread function calculations in Zmax using a Fourier transform. This is a very, very nice point spread function. It's got all the ringing of the Airy disk, so you can imagine it's a highly paraxial situation that I've chosen here. We can set up a situation where you see just how bad a given lens might be. We can ask, if I were to look, say, this far out, or this far out, or that far out, what fraction of the energy is captured? How far out do I have to go before I get 25%, 50%, 90%, whatever? And Zmax will plot for you what you actually got from any given lens configuration using a Fourier transform calculation of the point spread function, and what that nice Airy function would give you. And you can see the real trade-offs visualized. Some of the nice things about it is we can have them go through a real glass catalog. I can just say, all right, rather than n equals 1.5, let's use a given glass from a given real manufacturer, and they will take into account the dispersion, the variation of refractive index with wavelength. And although I don't use it in my class, if you were doing more detailed design, it would take into account the thermal expansion of the glass. It has a whole catalog of real lenses. I'm not a lens designer, so I am probably not the best one to say, oh yeah, here's a combo of lenses that will be perfect for this situation, but not that one. But there's a catalog of professionally designed lenses, like these two. What do I want students to get out of this? I'm not teaching optical design. I'm still just teaching an introduction to optics. But what I want them to do is, when I'm teaching them all of this paraxial optics, show them when it is and isn't good for real materials and real shapes. I want them to take away that unless they're prepared to do a whole lot of very detailed hand calculations and really delve deep into Born and Wolf, then they should probably use some software to actually model what's happening in their lens. And if all of your goal is to, if all you're trying to do is just get, say, luminescence from a sample to a detector because you're a physicist who uses optics rather than somebody who's designing optics for a client, well, you know, that can be a do-it-yourself project. If you're trying to design lenses for very high-resolution imaging, you probably need an expert. The main limitation of this is that once you get past point spread functions, it's not great for physical optics. You're not going to get realistic modeling of finite size diffraction gratings. It's not going to solve thin films, but it's still very worth using. So the current outline of my course is we do a couple weeks of paraxial optics. I'm still going to give them geometrical optics problems that are harder than just your freshman thin lens equation. But then we're going to do a lot of aberration theory, ray tracing examples, a lot of concepts from imaging, because my research when I'm not teaching is on microscopy. Then, because we're on the quarter system, this is only 10 weeks, so we still do a quick survey of wave optics. It's not as detailed as Ayrton's class, which is almost all wave optics. And then we do a week of microscopy applications. So that's the first half of what I'm going to talk about. The second half, since I like teaching with computation, I'm going to tell you about how I found a way to give English professors a heart attack. It starts off in sympathy with the English professors. I hate grading bad final project reports in computational physics. I hate it. It sends me ranting about the K through 12 system. But I can't expect someone to write a professional quality project report unless I'm giving them examples of it. So I decided to write one myself. Well, if I'm going to write a project report, I shouldn't just give them a journal article. That's not what I want from a computational physics class. So I looked around and said, what's a good project to do in computational physics? I said, you know, the double pendulum is fun to play with. I'll spend a little bit of time simulating a double pendulum, and I'll write a report on it, because that's always fun. You can generate pretty pictures. So here's a double pendulum. It's just two pendulums jointed together. And a simple question you could ask is, how much time elapses before the first flip? We're about to, it's going to start over. All right, so you see it takes a little while before the bottom one goes through a full revolution. Just watch. Almost there. It just went through a full flip. And you could ask, for different starting conditions, how much time does that take? And there are some starting conditions, the middle here, where you will never get a flip because there's not enough energy. And then it turns out that there are some starting conditions where it might take a little bit of time, or a long time, or a really long time. And rather than just having the time increase and increase and increase as you give it more and more energy, it turns out that there's a very complicated pattern here. And so if you were to color code how much time it takes, you get a fractal. And that's rather interesting. And I found this figure on Wikipedia, but there was no citation for it. There was an author cited, but there was no methodology for how they got it. And I said, well, you know, Wikipedia gives our colleagues in humanities and social science heart attacks. I'd better audit this. Now, Wikipedia is actually not necessarily that bad. Despite everything that gets fired at it, Nature did a study comparing Wikipedia with Britannica. It came out favorably. And interestingly, when I decided to look for other websites on the double pendulum, I didn't find any errors that I could notice on the Wikipedia page. But Wolfram's page, which is peer-reviewed and is not open source, actually had a glaring error in an equation. Also, my students and I have found that some of our work is cited on Wikipedia, so clearly it must be a good source. So here's what I found. I have the flip time color-coded in a grayscale on the left, and then if you threshold it at different levels to go from grayscale to black and white, you keep getting a similar fractal pattern. And it pretty much matches what's on Wikipedia. The reason for the differences, the reason why you get something very pronounced here and a really much smaller indent there, is that they did a double pendulum that was jointed. So imagine, you know, the two parts of my arm. You've got distributed mass, whereas I was in a hurry, so I just simulated ball and stick, where you've got 2 point masses. But you get the same qualitative behavior in either case. So I was having fun with this. The point of this is not just, look, I spent a bunch of time checking a Wikipedia page. I decided then, all right, for final projects, I won't require, but I will strongly encourage that people in computational physics pick Wikipedia pages that have citation-needed claims. So one of them picked a claim about the rings of Saturn. Anybody who's read about the rings of Saturn probably hears at some point that there are these gaps in the rings, and they have something to do with resonance. So we decided, all right, well, let's do a simulation. And you can find a resonance, but that doesn't produce a gap. Then we tried to destabilize the particle in the resonance by adding in another moon. And even when we added in another moon, we still didn't get anything to fly off. So what we were able to conclude is that it's a lot more complicated than the one-sentence description. I'd love to be able to say, oh, we got to the same level of sophistication as a planetary scientist in a 4-week final project for a course, but we didn't. But we at least were able to learn that one-sentence explanations don't always capture profound mysteries of nature. Who knew? Somebody else took a claim about the ability of IR to penetrate fog, and they just used a Mies scattering code to see if that's actually true and what really gives rise to that. Another person took a claim about another chaotic system and decided to try to reproduce some of the behavior. My observation was that the work and the progress was usually more focused, because instead of a final project starting with someone saying, I want to do something with a rocket, they would say, I want to do something with testing the claim that a rocket needs to burn fuel in this progression in order to achieve this type of trajectory or whatever. It also led them to realistic numbers. Instead of getting the question, I tried setting that parameter equal to 0.1 and then 0.2. What should I do now? They would say, well, I tried 5 and 6 because those are the actual more realistic numbers, and they could see whether it worked or not. The final products still spanned the usual range of quality, but at least they got there in a more focused manner. And they did come away with something else. I interviewed them, and I asked them about how this project went. And besides the usual thing of, well, the troubleshooting was really the hardest part, they usually came away not saying, oh, Wikipedia is right, Wikipedia is wrong, something binary. They said that the actual phenomena were too complicated to rate one sentence as right or wrong. That was nice to hear. And they actually became more trusting of Wikipedia if the page has citations, which is, again, more nuanced than just, well, Wikipedia is right, Wikipedia is wrong. So my conclusion from this half of the talk is that the internet actually has a lot of things on it that can make for very nice projects and classes, whether it's a computational physics class, as I just showed, or you could take it to a lab class and test someone's design. You could do an experiment to try to replicate any one of those numerous YouTube videos where people are doing demos that may or may not have video editing. Unchecked, unsupported claims actually make for great final projects. They're basically low-hanging fruit. So that's the end of my talk. Thank you.
Yeah,
how constrained were you by, I figure you'd be constrained by what you'd already taught them, language, techniques for computation?
So the biggest constraint is not the language. There's a lot you can do in computational physics if you just understand a few key programming concepts. The harder thing was that you're usually looking for things that can be done with ODE models or 2D PDs. I mean, doing time-dependent PDs in 3 dimensions requires usually more processing power and time unless you have a very well specified problem where you really know what you're looking for. So it was about that was the real constraint, is finding something that can be fact checked with simple techniques. You know, a claim for material science, well, we don't teach them how to do ab initio electronic structure calculations in the first computational physics class for obvious reasons. So, you know, it did have to be more, the nice thing is it had to be more day-to-day phenomena, not fact-checking a PRL or something. Although that would be interesting. Yeah.
Back to the plots that you made for the double pendulum, you mentioned that they are fractal. Do you actually get the same details if you zoom in on one point?
I did some zooming in to show it qualitatively, but more importantly, I calculated a fractal dimension, and I came out with pretty consistent fractal dimensions for different sets of initial conditions, and different sets of parameters, I should say. There was a question there.
So sometimes they say that finding a good problem is the biggest problem. How often does it happen that students come up with the problems which are too difficult, too long to solve? What's
the hardest part of a computational physics class is refining the final project topic. Because usually they start off with, it could be, well, here's an interesting one where they wanted to fact check something. A person had done some calculations about modeling Wi-Fi in an apartment and modeling the way that Wi-Fi propagates around obstacles. So we had to figure out, all right, you know, full three-dimensional vector solutions to Maxwell's equations are hard. You know, there's a reason why people could still write a dissertation on a better FDTD calculation. So, you know, we had to refine it. All right, well, we're going to solve a wave equation in 2 dimensions and see if at least qualitatively does an obstacle of roughly this size significantly inhibit propagation or not. You know, so we do have to refine it all the time. Somebody says, hey, I saw this thing about spin systems. Well, you know, you can go into a lot of depth on spin systems, or you can do the ancient Ising model or anything in between. So I have to push them to really consider how far they're going to go. So yeah, that is the hardest part, is getting them to refine. I find that initial topics are almost always too ambitious rather than unambitious. Yeah.
Did you end up with any students that ended up editing Wikipedia at the very end?
I think 1 or 2 of them did, but the hard part of doing that is if you find that, if your main conclusion is that the one-sentence statement isn't wrong, but not the whole story, then how much more are you going to contribute? And if you haven't explored it exhaustively enough, are you going to wind up putting your own unsupported claims into the paragraph that replaces the sentence? So they tended to avoid that, actually.
Okay, I suggest we continue the discussion at break. So before I release you, one of our own practice students has a few words to say about the workshop that happened
All right, great. Well, I've had the opportunity to meet a lot of you guys, but for those of you who haven't interacted with me, my name is Ben. I'm a first-year graduate student here at the college and the vice president of the Student Optics chapter. And I'm glad to have a chance to give you guys a really important announcement that we found out yesterday. So we found out we had applied for this thing called an IONS conference from OSA, the Optical Society. And for those of you who don't know, IONS is the International OSA Network of Students. It's conferences that student chapters get funding to organize and bring other students to the college to present on their research. And we found out yesterday that we got our funding approved, so that's pretty exciting. So 2016 in the fall, on those dates, Friday through Monday, so it's over the weekend, we're going to have